Alright, we'll now do our third problem in this topic, and this problem is taken from the textbook by Hiveler, Engineering Mechanics, Statics, and this is specifically example number 5.2. In this problem, it says that the operator applies a vertical force to the pedal so that the spring is stretched 1.5 inches and the force in the short link at B is 20 pounds. Determine the value of F at the reactions. I think this should be and the reactions at A. Okay, so here is our system. So this is the pedal right here, and then we have the short link. This is the short link, and this is the spring. Okay, and this pedal is supported by a hinge at point A. I mean hinge or pin. Okay, so we have reactions here, a pin reactions plus we have an unknown force. Okay, so therefore we are to find. I mean the problem asks us to find the reactions at A, the reactions at the pin, and then the unknown force F. Okay, and here I think we should first draw the free body diagram. Okay, so the first step is to draw the free body diagram of the pedal. Okay, so our system that we will consider for analysis is just the pedal, not including the spring and not also including the short links. Okay, so in drawing, okay, so right here we have a pin support, and if we convert, if we just show forth the reactions, then we have a reactions along X and a reaction along Y. Okay, so this is AY, this is AX, and right here we have a point. Right, that's 1.5. Okay, so from the center point to the spring, that's 1.5, and then another 1.5 for the short link. Okay, so if this is our system, then the forces that will be exerted by the spring is simply this force, right? And for the link, then another force like that. Okay, so this force is the spring force, and this one is given, right? It says here the force in the short link at B is 20 pounds. So this is 20 pounds. Now for the force exerted by the spring is simply the equation is just simply F. F is equal to K times the deflection or the displacement along the x-axis, because it says here that the spring is stretched 1.5 inch. So therefore F is just simply I will just write it here. F is just simply K times X. Now what is K? K is 20 pounds per inch. Okay, so this is given right here, 20 pounds per inch, and we multiply this by the stretched distance, which is 1.5 inch, and what we get is 30 inch. 30 pounds. Okay, so therefore this is 30. Okay, so we have AY, we have AX, and right here this is our unknown force. Okay, so looking at the problem, we have three unknowns, and we have three equations of equilibrium, and therefore the problem is determinant. Okay, so the next step is to apply apply the equilibrium equations. Okay, so what I'll do is to actually take moments at A. This is A, so take moments at A. By the way, we have to also label the distance. So this is 1.5 inches, 1.5 inches, and from point A to point F, this is 5 inches. Okay, so I'll take moments at A. Right, so summation of moments at A is equal to 0. Now my assumption is that all the moments that acts clockwise is positive or are positive. Okay, so first one is 20, right? Because that's the force that produces moments, right? So 20 times the moment arm, which is 3, right? So 20 times 3. Okay, this is clockwise, and the next force is the spring force, which is 30 times the moment arm. 30 times 1.5 now is equal to, okay, so in the right hand side of the equation, this one is counterclockwise. Okay, so force times 5. This is force times the 5. Okay, so take note that if I write the counterclockwise in the right hand side of the equation, this is positive. Okay, so therefore my force, the unknown force, is equal to 21 pound. Okay, and then another equation of equilibrium is summation of forces along y is equal to 0, and the assumption is upward is positive. So F, okay, so all the forces along the y is just simply F and AY, so therefore F is equal to AY. Right, so AY is equal to 21 pound. And for the summation of forces along X, which is equal to 0, right? So all the forces along X is AX is equal to 30 plus 50. Right? So AX is equal to 30 plus 20. So this is 50 pounds. Alright, our next problem is to solve for the internal shear. Okay, so this is problem 1.4, and this problem is taken from the textbook by Philpott, Mechanics of Materials, and this is example 1.3. Okay, so in that example, it was meant to solve for the stresses inside the material, but right here what we will do is just simply to draw the internal load diagram of the bar, because after all, as we have said, that in this course, or in the strength of material course, we are dealing with the stresses and strains which are internal, which are related to the internal forces. Okay, so this problem will help us develop our skills for that internal forces. Okay, so we have a bar right here, and this bar is actually loaded, just loaded along the x direction. Okay, so if this, let's say this is x, this is our y, and this is our z, the loadings is just purely along x. Okay, and recall that if the force is perpendicular to the cross-sectional area, so let's say I'll make a cut right here. Okay, so the forces right here are just purely axial. So therefore, our internal load would be axial. Now the question is, how do we find, right? How do we find the value or the magnitude of the axial force? Because we have this bar loaded at various points. Okay, so the first step is, right? So the first step is to draw the problem, okay, and its loadings. Okay, so this is our A, and this is our point A. and this is our point of loading. This is 25 kilonewtons, and right here we have another loading at C, and probably this is B. So at point B we have 80, right, 80 kilonewton, and right here we have 40 kilonewtons. Okay, so how do we determine the forces in each section? So first, let's solve for the support reactions. So that's always the case. If we have these external loadings, we have to find first the support reactions before we can solve for the internal forces. Okay, so solve for the support reactions. So therefore, if this is our forces, our reactions will be right here. So let's just say AX, since this is point A. Okay, so therefore, summation of forces along X is equal to 0, and let's assume that all forces going to the right is positive. So we have AX. Okay, so AX, okay, the next point is positive plus 80. Okay, and then the next point, this is opposite direction, so this is minus 40, okay, plus 25. 25 kilonewtons is equal to 0. So therefore, AX is equal to, so 80 minus 40 plus 25. So this is 65, right? Plus 65 is equal to 0. So therefore, AX is equal to negative 65. So that means that AX is 65 kilonewtons, but along the opposite direction. Okay, so now I'll redraw this and I'll make sections. And drawing the sections. Okay, so this is my first okay, so let's say this is point A, this is point B, this is point C, and this is point D. For the forces, we have 250, and right here we have 40, and this one is 80 kilonewtons. And in this reactions, we have this is actually going this way. So this is 65 kilonewtons. Okay, so what I'll do next is to make a cut. Okay, what if I want to solve for the internal force between A and B? Okay, so if that's the case, I want to make a cut anywhere along this, segment. Okay, so if I make a cut right here, so what I'll get is okay, so this is my support reactions, which is 65 kilonewtons, and right here at the section cut, we have an internal force. Okay, so this is my internal force, let's say P. Okay, and then if I want to check the internal force between the segment BC, so this will be my figure. so this is 65 kilonewton, and this one, this is 80 kilonewton. And also I'll have internal force P right here. And if I want to check the internal force between C and D, so as long as you have a cut, then of course you would need to expose the internal forces. Okay, so let's write this is figure, let's say this is figure 1 or figure 2, and then this one is figure 3, and this will be figure 4, for example. Okay, so the next step is to solve for the internal force P using equilibrium equation, using summation of forces along x, since this is just purely along x. Okay, so when we apply this summation of forces along x in this section, okay, so what we see is summation of forces along x is just simply P minus 65, right? So P minus 65 is equal to 0. So therefore P is equal to 65 kilonewtons. Okay, so let's write this is P sub 1, this is P sub 2, and this is P sub 3, right? So P sub 1 is equal to 65. Just simply applying the equilibrium equations, then you can obtain the internal force. And this arbitrary cut is actually it will produce the same value of P anywhere from point A to point B, because there's no loadings in between A and B, so therefore the internal force will just be constant. Okay, then if we apply the equilibrium equation in this figure 2, so what we get is negative 65, right? So negative 65, okay, plus 80, okay, minus 50, minus P sub 2, minus P sub 2 is equal to 0. But therefore, P sub 2, right? P sub 2 is equal to 15 kilonewtons. And for this figure 4, if we apply the equilibrium equation, we get 65, so this is minus 65, right, plus 80 minus 40, okay, plus P sub 3, right? So if we do this, what we get is 65 plus 40 minus 80, so we get a value of this will be P sub 3 is equal to 25 kilonewtons. Okay. Okay, so that's our actual force. So if we want to draw this, let's say I want to draw this actual force diagram. Okay, so this is our actual force diagram, and let's say this is the symbol is letter P for the internal actual force. Okay, so what this means is that it says here that our force, internal force from point A to B is just simply 65, and that is this is positive. Okay, so actual force, this is always, let's say if we make a cut, so this is positive as always. So tension is positive. Okay, so this is 65. So let's say this is alright, so this is 65, and then from point B to point C, this is 15. Right, so let's say this is 15, and then from point C to point D, we have a value of 25. Right, this 25. Oh, I think this should be negative, right? So this one should be negative right here, and right here is 25. Okay, so P is equal to 65, and right here this is right here this is negative 15. Right, so negative 15. It's a negative 15, and then right here we have a positive 25. Okay, so by just looking at the diagram, we can actually we can have a view of the magnitude of the forces along the bar. Okay, so that's the importance of the internal force diagram. And once we see, like for example, in design application, if we see this maximum value 65, then we can size up this bar. Okay, we can size up the thickness and the dimensions to accommodate this this maximum forces. Okay, so that's all in this video, and in the next video we'll be doing internal forces for shear and moments.